What I want to do is go back through discussion of sinusoids, complex numbers, and AC, and do this as kind of an overview slash review of what was on some of the previous PowerPoint lectures. This one won't be done with PowerPoint. I'll be doing it with the pen and the tablet. So just kind of a different way of illustrating things. So first of all, when we talk about AC circuits, AC traditionally standard for alternating current, but it's now used to describe both currents and voltages. And this is any voltage, we'll talk about voltage for now, that is expressed conventionally as a cosine function. And let me actually replace that with some Vm cosine omega t plus phi. We've been through this on the PowerPoint slides, but sometimes it's a little easier for me to illustrate things with a live blackboard lecture or chalkboard lecture. So Vm is referred to as the magnitude or amplitude. If you're from physics, you'd probably call this the amplitude. If you're from EE, this is the magnitude. This is omega. It is the frequency in radians per second. This is phi. It is the phase. So for a typical sinusoidally varying function, they repeat. So this is referred to as a periodic function because it repeats over some period t. Phi it's a phase. It's kind of like an offset from 0. So the normal cosine function would peak at 0. You can see this one, I was trying to illustrate here, peaks slightly later. So there's a little bit of an offset there. That would be the phase. If the phase angle is positive, the cosine function shifts to the left. If you have a negative phase angle, cosine function shifts to the right. Right is later in time, so this is what happens later in time. What happens at t equals 0 is right there at the axis. Periodic functions exist from negative infinity to positive infinity. Okay, this is usually given with units of volts. Omega has units of radians per second. There are 2 pi radians in a full cycle. So if you're talking about the unit circle, and you start here and you go all the way around, that's 2 pi radians or 360 degrees. So 2 pi over 360 is radians over degrees. So to convert, if you want to convert radians to degrees, this is the ratio that you use, or degrees to radians. So radians would equal, and we can reduce that, by the way, to pi over 180. So radians would equal degrees times pi over 180. Degrees would equal radians times 180 over pi. Okay, so that's how you convert back and forth from radians to degrees. Now, let me see. Let's see if I can't. I'm trying get a carriage return here. So let me get some new pages. Actually, let's see if I can insert a page break. There we go. And let's do some more, so I don't have to do this again. Okay, so the other thing we want to look at is we want to look at this frequency omega, which is given in radians per second. So in a full revolution, there are 2 pi radians. So if we take omega and we divide that by 2 pi radians per second, or sorry, just 2 pi radians. So omega has units of radians per second. We divide that by 2 pi radians, which would be the number of degrees in a full cycle. Then omega over 2 pi is going to have units of seconds minus 1, or hertz, and that's equal to f, the frequency in hertz. So f is the frequency in hertz, abbreviated Hz. Omega is the frequency in radians per second, and it's equal to 2 pi f. So the way you convert back and forth from radians per second to hertz is with this little formula here. So f obviously is omega over 2 pi. All right. It goes back and forth whether people use the terminology hertz or radians per second, but in the sinusoidal voltage, this whatever is multiplying t is omega. So let's look at a typical voltage. V of t, 10 cosine 2 pi t plus 30 degrees. Okay, in this case the magnitude is 10. And what that means is, in this sinusoidal function, that's your maximum and minimum value. So that's the magnitude. The phase, which is phi, the magnitude we sometimes call Vm. The phase, which is phi, is equal to 30 degrees. Omega is whatever multiplies t, and so in this case it's 2 pi radians per second. T is the variable. So you can see that this part of the argument of the cosine function is going to have units of radians, because you'll have radians per second times time. This part is going to have units of degrees. So if you wanted, for example, find the voltage at t equals 1 second, V of t will be 10 times the cosine of 2 pi times 1 plus 30 degrees. And so one of these is going to have to be converted. So if you choose the 2 pi, cosine of 360 plus 30 degrees. Obviously 360 plus 30 degrees in our case is the same as 30 degrees. The cosine of 30 degrees is 0.866, so it would be 0.866 volts. All right, and there are some examples that were worked out in the other information. Now we also talked about, to just kind of wrap things up, let's see, we talked about the period. So the period is the time it takes for the function to go through one full cycle, and that's defined as 1 over whatever the frequency is when the frequency is in hertz. Because the frequency is omega over 2 pi, we can also put t in terms of omega. So this is important too. All right, we also talked about phasors. So I want to talk a little bit about phasors. Let's first of all, just based on our Voltage is a function of time. What we learned was that the phasor transformation basically takes a voltage as a function of time and writes it as a voltage as a function of magnitude and phase only. So in this case, the magnitude is 10, the phase is 30 degrees. So this is our phasor equivalent. Okay, now let's talk a little bit about what the phasor represents. So a little bit of complex number math. Complex number is analogous to a vector. So we can actually come up with a plot for it. The phase angle, 30 degrees, is the angle that you make with the real axis. So 30 degrees, in our case, that's phi. And the magnitude is basically the length of the phasor. So it has a length of 10. And we can call that length just by writing magnitude of V. 30 is the phase of V. Or just write it like that, whatever the angle is of V. Now this 10 angle 30 is shorthand notation for 10 e to the j30, where j is the electrical engineering notation for imaginary. If you have, I have some students occasionally who are just insistent on using the notation I. We don't do that in electrical engineering because I represents current in electrical engineering. So we use j for the square root of -1 for the imaginary. You absolutely need to get used to that because from here all the way through senior electromagnetic fields, you will need to be familiar with the square root of -1 being j, not I. So learn to do it now so that you feel comfortable with it throughout the curriculum. Okay, so let's go back to this. So when I have this, remember it's shorthand here. Now remember there is an identity, Euler's identity. It says that e to the j phi is cosine phi plus j sine of phi. So in our case, we have 10 e to the j30. That's 10 times the cosine of 30 plus j times the sine of 30, which is 8.66 plus j times 5. Now because this is what we refer to as a complex plane, this 8.66 represents a coordinate on the real axis. And this 5 represents a coordinate on the imaginary axis. And so basically our 10 e to the j30, which we can also write shorthand as 10 angle 30, this is in phasor form. This is polar form of a complex number. This is rectangular form of a complex number. So this here is called a phasor diagram. All right, now let's talk about the application of this in an actual circuit. So we looked and we saw that basically we have two universes. We have the time domain and we have the phasor domain. Okay, and so this is of the form some function of time is some constant or magnitude times cosine omega t plus phi. This is the phasor, which in textbooks is written as bold. When writing hand notes, we use the squiggle to represent phasor. It's F naught angle phi, which one more time is shorthand for f sub 0 times the real part of e to the j phi, okay, where we have we've taken the real part only for temporary purposes, and then we go back and actually, you know what, let me just stay consistent with what I've said in the past, that basically this is shorthand notation for the complex number f sub 0 e to the j phi, and we'll just leave it at that. It's a little bit more simple because this does come out to be a complex number. Okay, so we go back and forth from time domain to phasor domain. So we have two different categories. We have voltages and currents, which means your V of t's are going to go to phasor voltages and your I of t's are going to go to phasor currents. And then we have R, L, and C. So resistors in the time domain remain resistors in the phasor domain. Inductors in the time domain become j omega L in the phasor domain, and capacitors become 1 over j omega C, which is often written as minus j over omega C. So you may be wondering how we get from here to here. If we have 1 over j, and we'll just say x, if we multiply that by j over j, that gives me j over j squared x. J squared is -1, so that becomes minus j over x. So if I have 1 over j times something, I can rationalize that by making it minus j over x. So just trying to fill in some of the blanks here that I didn't think were super well laid out in the information that came from the textbook. All right, so a brief illustration on how we might use this. So here's V of t. Let's just make an RLC circuit here. And we're going to let V of t be, we'll use our same voltage we've been using, 10 times the cosine of 2 pi t plus 30 degrees. Okay, so this illustration is what we refer to as a time domain circuit. And let's define an I of t here. So under normal circumstances in the time domain, if we wanted to solve for the current, we would have to write a KVL around this circuit, and we would have to express the inductor voltage as L di dt and the capacitor voltage as 1 over c times the integral of I of t dt. So we would have an integral differential equation, and then V of t would be our source, and it would be sinusoidal. So we would have a second order inhomogeneous differential equation that we would have to solve. And we don't want to do that. So what we want to do instead is we want to do a transformation. And we don't do it on the equation. We do it on the circuit. So V of t is going to get replaced with a phasor voltage, 10 angle 30. The resistor remains a resistor. The inductor gets replaced with j omega L, which in our case, given that L is 1, is going to be j omega, and omega is 2 pi. So that's going to be j times 2 pi. And then our capacitor is minus j over omega c, which is minus j over 2 pi times 0.5. So if we play with that, we should get minus j over pi. Okay, our current is a phasor current. So now, minus 10 angle 30 is 2 pi times whatever that phasor current is, plus j 2 pi times that phasor current. Oh, sorry, not 2 pi, just 2 missed that resistor. There's no pi there. Just thinking ahead. So this is the voltage drop across the resistor. This is the voltage drop across the inductor and the voltage drop across the capacitor. You put that capacitive impedance in there. So now we can solve for the phasor current. And let's see, I need a plus here actually, and that to equal 0. So if we move the 10 angle 30 over, it becomes positive, and then we can solve for the phasor current, that's going to be 10 angle 30 divided by 2 plus j times 2 pi minus j over pi. So that's going to be the current in the phasor domain. This is not a solution because at this point I'm going to have to actually do some complex number math and then transform back to the time domain. So let's try to do a couple more minutes on this lecture and see if I can get one more page in here, and we'll try to finish this example, and then we can, okay, why is this not letting me do this? Let's see here, okay. There we go. So let me try and go down to the bottom here. For whatever reason, this isn't wanting to let me do this. There we go. All right, so here I am. I is, somehow I lost this, so it is minus 10 angle 30 over 2 plus j times 2 pi minus j over pi. All right, so you would then leave this as minus 10 angle 30 in the numerator, and then in the denominator you want to collect your real terms and your imaginary terms. So this would be j 2 pi squared minus 1 over pi. Okay, let me get a quick number for that on my calculator on my other device. So we have 2 times pi squared minus 1 divided by pi. I get right here 5.96. We'll round it up to 6. Okay, so this denominator is 2 plus j6. So I is minus 10 angle 30 over 2 plus j6. Now 2 plus j6 on our complex plane, that's a real of 2 and an imaginary of 6. So in order to find the magnitude, I can use the Pythagorean theorem. And what comes out of that? Let's see, 40 square root 6.32. And then I can find the angle phi. Phi is going to be the inverse tangent of 6 over 2. So 3, trying to find my inverse command on my computer, and I'm not seeing it. Let's see. 3. That is just weird. Okay. Well, we'll just write it for now. We'll just write it as phi. All right. And then I'll grab a different calculator before we conclude the video. Okay, so I is minus 10 angle 30 over How am I getting minus? That should not be minus. That should be plus, because this moves over to the other side of the equal sign. So plus, plus, plus. All right. So now in the denominator we have 6.32 angle phi. Let me bear with me while I pull up another calculator and get the inverse tangent of 3. So let me do this real quick. Actually, don't seem to do anything real quick these days. Let me just open this up as quick as I can. Let's put it that way. So opening up my calculator. Here we go. Okay, I finally found it. All right, 71.6 degrees. So let me fill that in with 71.6. Okay, now remember, this is like e to the j 30 times 10 over 6.32 e to the j 71.6. And so following rules of exponential functions, you can move this one up to the numerator and make the angle negative. So we'll leave it in phasor form. It's going to be 10 over 6.32 angle 30 minus 71.6. All right, if we now fill in and do the actual calculation for the numbers, we've got 10 divided by 6.32, that's 1.58, so that is 1.58 angle minus 41.6. Okay, now all that we have remaining to do to get the current as a function of time is to do the inverse phasor transform. So I of t, take the magnitude, 1.58, cosine, omega is not going to change, so let's go back up and find what our omega was. It was 2 pi t minus 41.6 degrees. So now for the current, the magnitude is 1.58, the phase is minus 41.6. So if we were to draw a phasor diagram on the current, it would have a length of about 1.5 and an angle of minus 41.6. So there's your angle, there's your length. Our voltage was originally 10, angle 30. So our voltage would be like this, our current would be like this. All right, so remember we measure phase angles going clockwise when you have an angle less than 180 degrees. And if you start at the real axis and you look at the angle that is less than 180 degrees, the one that has the larger phase angle is what you call leading. So in this case, the voltage leads the current. And we'll do several examples of that. That's kind of a classic electrical engineering term used a lot in power systems. All right, I'm going to stop the video here, and then I'll do some more stuff for those of you